Section 2, Lesson 2, Part 2. We're going to look at the international system, the SI units, and look specifically at the different methods of measurement throughout the section. In Part 1, we learned about the purpose of the SI system and then how to convert between those different types of measurements using our stair-step method. Today we're going to focus specifically on how you're going to measure different types of things and what those are used for in science. If we're reading on page 51, we're going to pick up on the section titled Length. You should have your notes in front of you and be following along to complete each section as we read. Length. Length is defined as the distance between 2 points. Length measures with different tools can describe a range of things from the distance from Earth to Mars to the distance to a thickness of a human hair. In your laboratory activities, you usually will measure length with a metric ruler or meter stick. The meter, M, is the SI unit for length. 1 meter is about the length of a baseball bat. The size of a room or the dimensions of a building would be measured in meters. For example, the height of the Washington Monument in Washington, D.C. is 169 meters. Smaller objects can be measured in centimeters or millimeters. The length of your textbook or pencil would be measured in centimeters. A $20 bill is 15.5 centimeters long. You would use millimeters to measure the width of the words on this page. To measure the length of a small thing, such as a blood cell or bacteria or viruses, scientists use micrometers or micrometers, millionths of a meter, and nanometers, which is billionths of a meter. A long way. Sometimes people need to measure long distances, such as the distance of a migrating bird travels or the distance from Earth to the moon. To measure such lengths, you use kilometers. Kilometers might be most familiar to you as the distance traveled in a car or the measure of a long-distance race, as shown in Figure 8. The course of a marathon is measured carefully so that the competitors run 42.2 kilometers. When you drive from New York to Los Angeles, you cover 4,501 kilometers. Now, we're probably most familiar using the customary method of miles as our measurement. The kilometers would be the direct conversion to that in what would be the international system or the SI system or the metric system. On page 52, we're reading of volume. Volume is the amount of space an object occupies. Volume is measured in units, are created by multiplying units of length. Therefore, they are not base units, are not listed in Table 1. The cubic meter, meters cubed, length times width times height, gives you that volume. Shown in Figure 9 is the SI unit of volume. You can measure smaller volumes with cubic centimeters. To find the volume of a square or rectangular object, such as a brick or your textbook, measure its length, width, and height and multiply them together. What is the volume of a compact disc case? Well, you're probably familiar with a 2-liter bottle. A liter is a measurement of liquid volume of cube 10 centimeters by 10 centimeters by 10 centimeters holds 1 liter of water. 1 cube, 1 centimeter on each side holds 1 milliliter of water. So they're telling you that volume is easy to measure when it's a three-dimensional object that has distinct length, width, and height. If it's a square, if it's a rectangular object. However, if it's an irregular shaped object, such as a CD, how do you measure the volume of a CD? How do you measure the volume of something that doesn't have that regular shape? Well, that's where there's conversions between these. In the top of the page, it shows these 3 different cubes, blue, green, and yellow. The one all the way to the right, the yellow one, shows that 1 centimeter by 1 centimeter by 1 centimeter, 1 cubic centimeter is actually equal to 1 milliliter. So when you have milliliters or liters of a volume of liquid, that's actually the same space that it's taking up if you were measuring something in terms of centimeters, or as this cube shows, the green one in decameters and the blue one in meters, to show what those actually reference to. Now there's a second way to find volume. It's called volume by immersion. If you ever put something into water, or if you ever get into a hot tub, get into a pool, the water actually rises up because you are displacing, you're moving that water out of the way. Here's a second way to measure how you would find or calculate volume of an irregular shape. It's called volume by immersion. Not all objects have even regular shapes. How can you find the volume of something irregular, like a rock or a piece of metal? To do this, you're going to place the object into a known volume of water, find the volume of the water of the object together, and then subtract the smaller volume from the larger volume. Have you ever added ice cubes to a nearly full glass of water, only to have the water overflow? Why did the water overflow? Did you suddenly have more water? The volume of water did not increase at all, but the water was displaced. That means moved when the ice cubes were added. Each ice cube takes up space or has volume. The difference in the volume of water before and after addition of the ice cubes equals the volume of the ice cubes that are under the surface of the water. The ice cubes took up space and caused the total volume in the glass to increase. The volume of an irregular object can be measured the same way. Start with a known volume of water, drop in or immerse the object, increase the volume of water is equal to the volume of the object. So here you have two graduated cylinders, one that shows that the milliliter value is at 150. Then you're going to drop in this irregular shaped object, say this rock, and after you have measured that initial volume, you're then going to calculate the volume of the water with the object. So beginning volume, volume with. Now this item is immersed or all the way submerged into here, and you can see that from 150 it increased to, looks like, 180 as our milliliter value. So you had 150, 180. What's the difference? You would subtract those two and then take the new reference as your volume of the object, and there's a direct translation between milliliters and centimeters. So the difference was 30 milliliters. The volume would be 30 cubic centimeters for this rock as an example. The increase in the volume of water is equal to the volume of that object. On page 53, mass. The mass of an object measures the amount of matter in the object. The kilogram is the SI unit for mass. 1 liter of water has a mass of 1 kilogram. Smaller masses are measured in grams. 1 gram is about the mass of a large paperclip. You can determine mass with a triple beam balance, shown in figure 10. The balance compares an object to a known mass. It is balanced when the known standard mass of the slides on the balance is equal to the object of the pan. Why use the word mass instead of weight? Weight and mass are not the same thing. Mass depends only on the amount of matter in an object. If you ride in an elevator in the morning and then ride in the space shuttle later that afternoon, your mass is the same. Mass does not change when your location changes. Weight, however, is different. Weight is a measurement of force. SI units for weight is the Newton. Weight depends on gravity, which can change depending on where the object is located. A spring scale measures how a planet's gravitational force pulls on an object, and several spring scales are shown in figure 11. The most common one is probably the one that you step on to show how much you weigh in terms of pounds. Now that same weight in terms of pounds is actually a measurement of the gravitational force pulling on you. If you ever were to travel to other planets, your weight would change even though you would still be the same size and have the same mass. This is because gravitational force is different on each planet. If you could take your bathroom scale, which is used as a spring to each of the planets in the solar system, you would find that you weigh much less on Mars, much more on Jupiter. A mass of 75 pounds or 34 kilograms on Earth is the weight of 332 newtons. On Mars, the same is 126 newtons, and on Jupiter, 782 newtons. So based on the gravitational force of whatever planet you're on, in this case, in this scenario, would be the actual weight that you carry. So your weight can change because it's based on the gravity that's pulling on you. If you're on the moon, there's less gravity. You can see astronauts in their depictions of going to the moon jumping in the air, and there's less gravity. They can actually have quite a bit more hops or elevation to each of their jumps because there's less gravity pulling on them. Therefore, they weigh less and have that weightlessness as they are moving up and down. Let's take a look at the difference between mass and weight one more time. In summary, the difference between mass and weight can be calculated by taking a look at this chart. What is mass a measure of? Mass is a measure of the amount of matter in an object. It's measured in kilograms, and it is always going to be the same. Weight, however, is a measure of the force that is on an object. It's measured in newtons. A lot of times we're going to call this pounds in terms of our customary system, and it's not the same everywhere. Your weight can change based on the gravitational force of whatever object you're on. So if you're on Earth, your weight is different than compared to being on the moon or on Mars or on Jupiter. Now, here's a question for you to think about. Does air have mass? Yes or no? Well, is air matter? Well, yes. So therefore, it has to have mass. If it doesn't, if it's not matter, then how do we use it to breathe? How do we use it to survive? Even though it weighs barely anything, obviously, if you have a volleyball pumped up with air or a basketball pumped up with air, it's a piece of rubber full of air. It's not very light, and it's used for these different athletic activities. But because there is something to it, it creates and takes up space. It has matter. It also has mass, even though it weighs almost nothing, or it has the mass of almost nothing. It's very, very, very light in terms of its overall amount of matter and its overall weight as relation to its gravitational force. But air does have mass. Air is mass because it's made up of matter. On page 54, Let's sum up our reading in looking at the different ways in which we measure temperature and then time and rates. Temperature. The physical property of temperature is related to how hot or cold an object is. Temperature is a measure of the kinetic energy or the energy of motion of the particles that make up matter. So all these little particles inside of each thing bouncing all over the place, that's the measure of an object's temperature. Temperature is measured in SI units with Kelvin, K. The Fahrenheit and Celsius temperature scales are the most common scales used on thermometers and in classroom laboratories. These two scales do not start at 0, as shown in Figure 12. A 1 K difference in temperature is the same as a 1 Celsius difference in temperature. So you can see these three scales both in your textbook and on this page that show the difference between what these measurements are. We're most commonly going to use Fahrenheit in the form of our measurement of temperature. We know that water freezes at 32 degrees. We know that water boils at 212 degrees. Those same measurements, those same marks can be seen here in terms of Celsius and Kelvin, which are probably most accepted in the scientific community. Celsius at 0 is our freezing point, and at 100 degrees is our boiling water. You notice that there's a bigger difference between these. There's 100 calculations between Celsius and that distance, and 32 and 212. There's 180 different calculations between those, or different degrees between those. So Celsius degrees are actually a different scale, are a little bit larger than what would be considered each Fahrenheit degree. Now Celsius and Kelvin match up perfectly. From 273 to 373, there's 100 degrees difference and 100 degrees difference, so these two are easily converted. There's a little bit more math calculation that goes in between converting those different temperature rates. Time and rate. Time is the interval between two events. The SI unit of time is seconds. Time also is measured in hours. And can you imagine hearing that a marathon was run in 7,620 seconds instead of 2 hours and 7 minutes? A rate is the amount of change of one measurement in a given amount of time. One rate you are familiar with is speed, which is the distance traveled in a given amount of time. Speed often are measured in kilometers per hour, or in our case, miles per hour. And these unit that is changed does not necessarily have to be an SI unit. For example, you can measure the number of cars that pass through an intersection per hour in cars per hour. Rate is basically two measurements that are put into this fraction form. We're again most commonly used with miles, a distance, per hour, a time, or kilometers. You can see that in any type of speedometer here, you've got a miles per hour measurement, and then right below that in the smaller lettering, you actually have a kilometers per hour measurement showing that metric system. A rate, again, is a comparison between those two different measurements, one of those measurements changing in a given amount of time that is used as its second reference. Your homework is to complete the SI units worksheet and to practice with customer unit conversions on IXL.